Greetings, everyone. Today I've got 5 example problems for you, all about rotation. All the example problems are pretty easy, though. In fact, here they are right here. This is all 5 example problems. So, I hope that made sense. Pause the video if you need to, and I'll see you next time. Just kidding, we're actually going to go over them. First example problem, we've got a bicycle tire like this. We've got 3 different forces acting on that bicycle tire. First one, force A pulling down at that point, force B pulling diagonally at that point, and force C pulling down at that point. And I give you the distance to the center of each of those, and I ask you to find the net torque on the entire wheel from all 3 of those forces. Well, we can start working on that. Torque net, well, that's just going to be the torque from each of these put together. So torque A plus torque B plus torque C. And torque is R cross F in each case. So we've got and so torque is R cross F, but it's also RF sine theta, like that. We should take a look at each one of these individually and figure out what contribution each of them will have to the total. So I'll start with torque A. We can figure out what torque A is going to do for this. Well, we're probably going to end up using just this RF sine theta to figure this out. The one thing that RF sine theta does not have is indicating what direction this would be. See, when you have the cross product like this, you retain the direction if you do all the math right, but without the cross product, you're only getting the magnitude, and you have to do something else to figure out the direction. We can figure out the direction with the right-hand rule, though. So remember the right-hand rule. We take our fingers and we put them at the center of rotation, here. And we move our fingers towards where the force is being applied, over here. So I move my fingers over that way, and then once I get there, I rotate my fingers to be pointing in that direction while keeping the rest of my hand kind of going in the same direction. So the rest of my hand is still going that way, but I've rotated my fingers down like that to match the force, and then I extend my thumb, and that tells me the direction. My thumb is coming out of the page when I do that, so I'm going to leave the torque as being positive for this. I'll define positive is out of the page, so out of the page is going to be positive. So it'll be positive RF sine theta. Okay, well, radius is 0.3 meters. 0.3 times force. Well, force is 12 newtons. 12 newtons. Times the sine of theta. This is where it gets interesting again. We've got to determine what the sine of the angle is for this. Remember how we do that? We take a line going from the center of the object out to where the force is being applied. So line going from the center out to where the force is being applied. And we measure the angle between the two objects, between this line and this line. And that sure does look like a right angle to me. So this is going to be the sine of 90, and the sine of 90 is 1. So we just have 0.3 times 12. And that's going to be 3.6. What were the units for this? Well, let's see. It should be newtons times meters. Newton meters. Positive. Okay. Torque B. Well, let's take a look at torque B. Torque B is going off this way. Now, is that going to be positive or negative? Okay, I need to take my hand and start at the center start at the center and move on over to where the force is being applied, and then keep my palm going the same direction, but move my fingers towards the direction of that torque, and again, it's out of the page. That's one way of doing it. You could see how awkward that was, moving my hand around like that. The other way to do it is to just say, well, it's going around like this. If it's going around like that, if this force is going around like that, then it's going to be out of the page, like that. Like that. It still works. This is going to be another positive one. Positive. Okay, radius 0.3 meters times force 16 newtons times, oh, we need to have the sine of theta here. Take a look at this and tell me what you think about the sine of theta. Where is theta? What is theta? How are we going to find that? Is theta just 60 degrees? Is it 30 degrees? Look at how I've drawn this here. And remember how we draw or how we find the angle. I'll give you a second to think about that before I go on. Okay, let's find this angle, and it's going to be just like we did before. We've got a line starting from the center and moving out to where the force is being applied. Now tell me, what does that angle look like to you? That angle in there? Well, to me, it certainly looks like 90 degrees again. If you can't tell, generally it's going to be 90 degrees. If it looks like it's 90 degrees, it's probably going to be 90 degrees unless they've given you some other information. Clearly, this angle in here is not 60 degrees. If I rotate it like this, it becomes pretty clear that you've got this line, and they are right angles to each other. So that's another 90-degree angle. Isn't that interesting? It's not 60 here. It's 90. This angle here doesn't make any difference. You could have a force going off on that kind of diagonal, or this, or this, or this, and as long as you have a 90-degree angle, in any of these places, it's going to be a 90-degree angle that you plug in to sine of theta. It doesn't matter where you are along this outer rim. If you are perpendicular to the outer rim, then it's a 90-degree angle. So that simplifies things quite nicely, in fact. This is another 1 right there. And so 0.3 times 16 is 4.8. And it's going to be Newton meters again. Okay, torque C. What's torque C going to equal? This one is particularly difficult to do this one right there, because I have to kind of hold it like this, take my fingers, start there at the center, move them towards where C is, and then point my fingers in the direction that C is going, and it's hard to tell, but my thumb is going into the page when I do that. So into the page for my thumb means a negative torque. You can also think about it like, if C was the only force on this, pulling down like that, then the wheel would turn this way, and that would get me an into the page torque. So this is going to be our negative torque, and this one is going to be 0.1 meters times 4 newtons times, what's the angle? Well, I think you can tell if we start there and move there, we're going to get another 90-degree angle. And so we've got the sine of 1 again, and so, or sorry, sine of 90, which is 1, and so we get 0.4 Newton meters. Sometimes you will get other angles. If you got an angle on this that was, for example, starting there and moving out like that, or something starting there and moving in like that, these two here are not going to be 90-degree angles, because you start at the center, you move out, you measure this angle right there, or you start at the center, move out, and you measure that angle right there. Obviously, neither of those are 90 degrees. Most of the time, it's going to be 90 degrees going around circles like this, though. But do be careful for things like that. All right, what do we do after this? Oh, I already saw a mistake. I forgot that negative sign. Thank you if you're yelling at the screen because I forgot that negative sign. All we do is add these up at this point. So we've got 3.6 plus 4.8 minus 0.4, and we get 8 Newton meters. So torque net is 8 Newton meters. What does that mean? Well, it means that after all is said and done, we've got 8 Newton meters of torque that are going around like this, around like that. Thumb out of the page because it's positive 8. You'd go around like this, and so you'd have 8 Newton meters of net torque trying to make the wheel spin in this kind of direction. The book actually has a whole lot of good examples. It's just that most of them are explained very poorly in the book. You may have noticed this as you're going through the book. So sometimes I just give you an example from the book, but hopefully I'm going to explain it slightly better than the book does. This is example 10.2 from the book. We've got a disc that's 50 kilograms, radius 0.06 meters, and it can spin around freely about its own center. There's a cord wrapped around it, and that cord is being pulled on over here with a 9 Newton force. We need to find the acceleration of that cord as it's pulled off that way. Well, what kind of problem is this? If you have to find an acceleration of something, there's a good chance that it's going to be kind of a force problem, maybe. If you're looking for an acceleration, it's probably going to be forces, maybe kinematics, very likely forces. Well, this is rotating, though. If you've got something rotating, it's not really forces that we should be concerning ourselves with, it's torques that we should be thinking about. Even though this is an acceleration, we should be looking for a torque on this. We can start with torque net is equal to I alpha, which is our stand-in for F net is equal to ma. Then we can remember also that torque is equal to R cross F, which is also R F sine theta, as long as we can remember a direction. So I'm going to, well, actually, let's look. What are all the torques acting on this? For something to be a torque, it has to be a force applied at some distance away from the center. The only option we've got is this thing. That's the only torque available for us. So I'm going to plug in this in for the net torque, because the net torque, it's just all the torques added together, and that's just that one thing right there. So now we've got R F sine theta is equal to I alpha. Okay, what's I? Well, I, this is a disk. You'll remember this eventually, but it's 1/2 mr squared. And then that's the moment of inertia for a disk. And then alpha, what's alpha? Alpha, you can look up in your equation sheet, that's A over R. Now we've got this thing. What can we do with this? We're going to try to find A eventually. Well, I can see that we can do something over here. We've got R squared and R, so those go away. And then we've got an R and an R, so those go away. And we've got force times the sine of theta is equal to 1/2 m times A. Force sine theta is equal to 1/2 ma. We need to figure out what the angle is. Well, I've kind of hidden it here, but you can imagine that the string must be coming around like this on here, inside, just barely inside the spinning disk. So where is the force really being applied? The force is being applied where the string loses contact with the rotating wheel. And so if I go here and I go up to where it's probably losing contact, something like that, it's going to be another right angle. If you've got a yo-yo or a spinning disc or something like that, and the string is being pulled off of that spinning disc, the string, imagine this is a yo-yo, does the string kind of just wrap around the yo-yo like that for a while and then go like that? No, it doesn't have a weird jump like that. It doesn't go around and then go at some strange angle off of it. It goes around and then up like that. That's a yo-yo string right there. And that is at a 90-degree angle to that. If that's the point at which the string leaves the yo-yo, that's a 90-degree angle. These other two would not be, but that one definitely is, and so is this 90-degree angle. If this is a 90-degree angle, then that's another 1 again. Our force was 9 newtons times 1/2 times mass of 50 times the acceleration, which is what we're looking for. So we can get out our calculator, and we can say 9 divided by, it looks like that's going to be 25. And we are going to get that the acceleration of this is 0.36. What are the units? Yeah, meters per second squared. Now, what is accelerating here? Well, you would not measure the disk accelerating. You'd measure the angular acceleration of the disk, not the linear acceleration. This must be the acceleration of the string, not the disk. We can also find the acceleration of the angular acceleration of the disk by remembering that angular acceleration is a over r, and if a is 0.36 and r is 0.06, then I think that you can tell that this is going to be 6 radians per second squared. Here's the next example problem I wanted to give you. It's going to be very, very similar to example 10.3 in the book. We've got a mass here connected via a string, which is strung around this solid sphere. In the example in the book, it's another disk, but we've had so many disks recently that I wanted to give you something different. So instead, we've got a solid sphere there that this is wrapped around, and the sphere can rotate freely. The sphere has a radius r and a mass ma. We need to find the acceleration of that block as it falls down. Wow, what kind of problem is this? I've got a spinning thing, so there's definitely going to be something with angular something. I'm trying to find an acceleration. Okay, if there's a spinning thing and there's an acceleration, I'm probably going to have a torque, because, you know, torque involves forces and torques on spinning things. And the torque equation gives me the angular acceleration, but I can convert that pretty easily into the linear acceleration, like this is asking for. But also, this is not the only thing that's moving. We've also got that mass B that's moving. This isn't spinning, so this is just going to be F equals ma. We've got two objects here, and whenever we have two objects, we're probably going to have two kinds of equations. Very often, previously, it was just two different F equals ma's. Remember the Atwood machines that we talked about? We often had two different F equals ma equations. This is kind of like an Atwood machine, except there's no second mass. There's only this heavy sphere up here. Well, now we're going to have a torque equation for this and a force equation for this. So let's get started. The torque on the net torque on A is going to be the moment of inertia of A times the alpha of A. We've never made torque diagrams before, but let's make a quick torque diagram. Here's A, the sphere A. I'll list all the torques acting on it. Okay, done. Yep, that's it. So, what is this? Well, that's the torque generated by the tension of that string. So that torque is actually the tension in that string. Now we can say, okay, torque net, well, I remember that torque is equal to R cross F, which is RF sine theta. And so I can go down here and I can replace torque net with RF sine theta is equal to the moment of inertia of A. Well, the moment of inertia of this sphere is 2/5 mr squared. Look that up in the book to get that 2/5. It's always mr squared. I is always mr squared, but there's always a different fraction out front. And the book has that table that I showed you. Times alpha. We don't really care about alpha. We're trying to find A. So I remember that alpha is equal to A over R and, oh, not squared, A over R. There's a little bit that I can do here. I can get rid of one of those R's and another one of those R's. Oh, it looks like that radius never mattered. I was going to plug in that radius everywhere, but I'm not, because it doesn't matter anywhere here. Need to figure out theta. Well, I start in the center, I move over to where the string is coming off, and I see that that's a 90-degree angle. Like it always will be when you've got something spinning like that. Because of a string, that is. So this is equal to 1. And what kind of force is it? That's the torque. So I should replace that F with a T because it's the torque that's acting on it. And that is equal to 2/5 times the mass of A times the acceleration. Now, is this acceleration positive or negative? It's going around like this, and so my thumb is pointing out, therefore it's going to be a positive acceleration according to this. Let's do the same thing for the forces acting on B. So this is for this object here. F net is equal to ma. What are all the forces acting on B? Well, we need to draw the free body diagram. We've got tension, and we've got the force of gravity. And what's the force of gravity equal to? mg. I'm going to define up to be positive, and because I'm defining up to be positive, it's going to be what minus what? Okay, so if I'm replacing F net with forces, it's going to be the tension, because that's going up, minus the force of gravity, which is mg, because that's going down. And this is going to be the mass of B, and this is equal to ma, so that's the mass of B, times the acceleration, but the acceleration is down. This block is going to be going down, and so I need to have a negative acceleration there. I've defined up to be positive. I know that we're going to have a downward acceleration, so I have to replace that with negative a. Now, I've got two equations. This one for the sphere, and this one for the block. I can take this torque, or sorry, this tension, I mean, and plug it in right there and solve for A. So now I've got 2/5 times MA times A minus MB times G is equal to negative MB times A. I need to solve for A, so we've got 2/5 times MA times A plus MB times A is equal to MB times G. Need to solve for A. A is going to equal MB over 2/5 MA plus MB times G. Well, does this make sense? MA is our sphere that everything is wrapped around. A, B. If the mass of B was 0, if this was just replaced by a single atom, well, we'd get rid of this and we'd get rid of this. Those two would go away. Well, you'd have 0 over whatever. I don't even care what that is because the numerator is 0. It wouldn't accelerate at all. If you took B away, there'd be no acceleration here. Done. That makes sense. If you had a mass of A was 0, if the mass of A was 0, if this is a perfect pulley with no mass, no inertia, anything like that, then the mass A there would go to 0. You'd get mass of B over 0 plus the mass of B. So that'd be mass of B over mass of B. That would be 1 right there, and the acceleration would just equal the acceleration due to gravity. If this was a perfect sphere that with no mass or anything like that, then B would just fall down at the normal 9.8 meters per second squared. So this equation makes sense, and we have shown that it makes sense by doing this kind of analysis on it. I always encourage you to do that kind of analysis when you're doing these problems. Make sure that your answers make sense, especially when you've got a purely variable, purely symbolic answer like this. Here's the next example, example 10.6. We've got a yo-yo on the end of a string, as yo-yos often are. If you have a yo-yo, go ahead and start playing around with it and see what you can do with it. If you hold the string in your hand and let the yo-yo unravel, unwind down, you'll see that the yo-yo does not fall at 9.8 meters per second squared. It falls slower than that. You can hold the yo-yo in one hand and just a rock in the other, and let the yo-yo go while holding onto the string while letting go of the rock, and the rock will hit the ground first. Can we use the physics that we've learned to figure out how fast the yo-yo is accelerating? The answer is yes. And can we figure out what the tension in the string is going to be as you drop the yo-yo? Again, yes. Well, what kind of problem is this? There's definitely something spinning, and so it's probably going to involve torque. But it's not just spinning, it's also falling. That is going to involve regular acceleration, which is going to be just F equals ma. When you've got something spinning, when you've got something spinning up faster and faster, it's probably going to involve torque. If you've got something falling down, it's probably going to involve F equals ma. In this case, we're going to use both of those to figure this out. We're going to start with torque is equal to I alpha, net torque. Well, what are the torques acting on this? Sure looks like there's just one thing. I'll draw the diagram. Here is the yo-yo. The force of gravity does not apply a torque because the radius there is 0, but that tension there sure does apply a torque because there is a radius there. So the torque from the tension, torque from tension, is going to be the radius at which the tension is being applied, which is radius r, times the force of that tension, which is t, times the sine of theta, and again, we've got a right angle in there, so that's just going to be 1. So the torque due to tension, which is the only torque available to us, is going to be RT. So we can take this and say that this side is RT, and that's equal to I. Well, what shape are most yo-yos? Most yo-yos are disks. So I'm going to assume that this is a disk, and the moment of inertia for a disk is 1/2 mr squared. The mass of the yo-yo is m, the radius of the yo-yo is r, and this is all times alpha, and alpha is a over r. Again, we get lucky and we can see that that cancels with that, and that cancels with that, and therefore the tension in this is equal to 1/2 ma. I want to find T and I want to find A individually, not together like this. This is the relationship between them. But I want to find tension as a function of something and A as a function of something else. And I don't want to have to relate them two together like that. So we need to do another step. And that next step is going to be F net is equal to ma. Now, what's the net force on this? We've got our yo-yo, we've got our tension, and we've got our force of gravity, which is mg. This time, we don't have to care about how far from the center the force of gravity is being applied. The force of gravity is always applied at the center of an object. And so gravity often will apply no torque, but sometimes it will, and we'll actually talk about that later. In this case, no torque because it's at the center. But the tension definitely isn't, but we don't even care because this is forces and we have to include both of them. Let's say that up is positive as usual. So we've got the tension minus mg is equal to negative ma because it's falling down. That negative is very important here. We can plug in this in there, this tension right there. So now we get 1/2 ma minus mg is equal to negative ma. We can solve for this and get 1/2 ma plus ma is equal to mg. After moving things around, the m's go away. We get 3/2 a is equal to g, or A is equal to 2/3 G. Is that reasonable? I think it is. When you drop your yo-yo, it's not going to be going down at full speed, but it's going to be going down at a decent clip. 2/3 G, that makes sense. With a tiny little bit of paper that I have left, because I'm still trying to save trees, we can figure out the tension. Tension is equal to 1/2 m times A, but A is 2/3 G. That cancels with that, and we see that the tension is equal to 1/3 mg. If you are holding onto this yo-yo as it falls down, then the tension that you have to apply is going to be just 1/3 of its normal weight, of the normal force of gravity as it's falling down. And that also makes sense, that it's going to be less effort for you to hold the yo-yo up as it falls down, because it's mostly still falling down. And it also makes sense that if you've got a fraction 2/3 there, you're probably going to have a fraction 1/3 there to make up for it. That is example 10.6 from the book. And this is example 10.4 from the book. It's going to be very, very similar. We've got the same yo-yo. Same mass is equal to m, same radius is equal to r. Instead of finding the acceleration or the tension, we're going to find the velocity of this object after it's fallen a height h. What kind of problem is this? I'll actually let you pause right here and try to think about how you would solve a problem like this when you're trying to find v. Thinking about what we've talked about recently, how are we going to find a v? I hope you can see from these hints, we're trying to find a v after falling h. That's probably going to mean that we need to use energy here. If we're finding a velocity, that's much more likely to be an energy problem. If we're finding acceleration, it's much more likely to be force or torque. But velocity, especially a velocity after falling a certain height, that is much more likely to be an energy problem, because you can find energies really easily. We've got heights, we've got velocities. This is going to go into some kind of gravitational potential. That's going to go into some kind of kinetic energy. We've got delta E is equal to W. Is there any work being done on this from the outside? Well, no. So delta E is E final minus E initial. So E initial is equal to E final. My E initial, what are my initial energies? My initial energy, well, this thing is going to originally be somewhere up here, and it's going to fall a distance h. So I'm going to say that it's going to end up at a height of 0, and it's going to begin at a height of h. So that means that I've got UG initial there. What about my final energies? My final energies, well, I've lost all my gravitational potential when I've fallen down a height h, but now I've got some kinetic energy. It's falling down, so I've got kinetic energy, and I've got rotational energy from it coming down. So I've got kinetic energy, final, plus rotational energy, final. I can take this and plug it in there, and I can take this and plug it in there. I get UG initial is equal to KE final plus RE final. MGH is equal to 1/2 mv squared plus 1/2 I omega squared. I can't cancel the m's quite yet. MGH is equal to 1/2 mv squared plus 1/2. I'm going to say this is a disk again because disks are easy, times 1/2 mr squared, and because the moment of inertia of a disk is 1/2 mr squared, times omega. Omega is v over r, but it's squared. So cancel out those r's, and now we can cancel out the m's. Excellent. GH is equal to 1/2 v squared plus 1/4 v squared. You'd better know that that is 3/4 v squared, so I'm solving for v. V is going to be the square root of 4/3 GH. After the yo-yo has fallen a height h, it's going to be going at a speed of 4/3, a square root of 4/3 GH. This is example 10.4. It is very important that you start learning the difference between what an energy problem looks like and what a torque or force problem looks like. There's unfortunately no real way for me to just explain to you, like, oh, here's 3 clues to look for, and that's it. It really involves looking at a whole bunch of example problems and doing a bunch of problems from the book and getting a feel for what type of problem is what and what type of problem is something else. Often you'll have problems that require 2 different kinds of things to solve them. And really, the only way you get that is by doing example problems yourself. I can tell you that if you have a bunch of velocities or heights, then yeah, it's probably going to have energy in there, at least somewhere. But there's so many different permutations of problems like this that it is very difficult without doing example problems yourself. So I strongly encourage you to do the example problems that I have listed in the announcements. Good luck, everyone.